Now it's good. Yeah, now it's good. Okay. So first of all, this is an overview of the current OPV record efficiencies from square millimeters to 800 square centimeters. The current record at 3 square millimeters is 18.2%, whereas at 800 square centimeters, it is 8.7%. That is a large discrepancy. And you can see when you go from 3 square millimeters to 1 square centimeter, you already lose from 18 to 15% at the moment. That's quite a lot, and both are cells. Then obviously we change to the module level, we lose again, and increase the size of the module and we lose. So the question is, what is wrong with OPV? Is something wrong with OPV? Is it not upscalable? There are general issues upon upscaling. One thing is that different groups are specialized on different device areas. The ones working on square millimeters are not the same groups that are working on square centimeters, modules, and so on. So processes, materials, everything needs to be interchanged in between groups and labs, and the reproducibility is not always very good. Also, a lot of people work on small area devices, but not that many work on larger area devices, which means that the manpower is on the small device level. The larger devices just progresses slower because less people work on it. This is an obvious thing everybody knows about. The small cells are made with a spin coater. The larger ones, you need a doctor blade. If it gets even larger, you need to accelerate it, or you need a slot die coater. That's a change in process, which is especially when comparing spin coating and doctor blading is a big change in the film formation process. Another thing is that statistics are really mean. A person working on square millimeters is happy about this result, can present a HIERN device with 14.5%, not caring about the mean value, about the statistics of the other devices. The one HIERN device is the good one, but the poor guy who needs to upscale this to square centimeters is having a really hard time because there's absolutely no possibility for him to reach 14.5% if only 5% of the area is working with this percentage. So you have to live with the mean value, and this is only the best case actually, because this does not include defects or something like that. So in the case of small area devices, defects which whatever destroy and completely shunt your devices, 5% of your devices, that's just a yield thing, and they are basically discarded. If you go to large areas, you cannot discard those, and what just lowers your yield on a small device level lowers your performance on the small area device, on the large area device. Also, the film homogeneity, if you increase the area, is harder to obtain. And then, of course, there's an obvious change when going from cells to modules. You need additional processes. You need a structure where you can interconnect your individual cells. You need a patterning process. All of your materials layers need to be compatible with this. You introduce another resistance, the interconnect resistance. You cannot make it infinitely small because all the current will go through this resistance. Obviously, you have the geometric fill factor, which automatically causes a direct loss of your performance. And you cannot go, the cell width plays an important role. And that is actually the only technical detail I will present, which is the limitations due to the ITO sheet resistance, because this is a problem on different levels. If you take a 17.6% cell on a square millimeter and you try to upscale it to a 1 square centimeter cell, like the Fraunhofer did, there are intrinsic losses due to the ITO sheet resistance, which you cannot evade. You can play around with the geometry. You can try to minimize those losses, but there are several percent losses just due to the ITO sheet resistance. And if you go to the module level, this becomes even bigger of a problem, because for a cell, you can extract to 2 or 3 different directions with the bottom electrode, but for a module, you only have one direction, so this becomes even bigger of a problem. And on the one hand, the sheet resistance of the ITO directly causes a loss, a power loss, because you have a resistor, you have a current flowing, you have power loss. But on the other hand, it also causes a voltage drop underneath your cell, which automatically means that your cell cannot work in MPP throughout the whole area. And in this case, an interesting statement would be the flatter the power curve around the MPP, the more beneficial it is for upscaling this system. Because, yeah, you always work around the MPP and not directly in the MPP. Then finally, when going to even bigger areas, which is mainly done by industry in the end, of course, you have to deal with a lot of more problems because roll-to-roll processing for OPV becomes the method of choice, the technique of choice. So you have to deal with a lot of problems. I listed everything I could think of here, marked the ones red, which cause big problems, mark the ones which are not that dramatic, rather green, and intermediate yellow. So one thing is the change of the substrate, which transmission-wise is not a big problem, but all of a sudden you don't have glass anymore, which means you need an encapsulation, which means you need an additional layer to your substrate on the front contact. Also, you cannot use ITO anymore because it's too brittle. You need structures like IMI, which are less transparent, or silver nanowires, which cause other problems. Non-halogenated solvents, obviously, due to legal reasons. Slot die coating is not that much of a problem if you have doctor blading before, but the coating in air may be a problem. Annealing in air is definitely a problem. Working at lower temperatures due to the plastic substrate may be a problem because you cannot anneal at 200 degrees or whatever. A very big problem is the materials you use and the layer stack, especially the HDL nowadays. Yeah, everything on the small level works with evaporated molyoxide silver. And yeah, the community is having a hard time to find fully solution processable stacks for the new materials. And yeah, this includes the printed top electrode. And of course, the larger you get, the more expensive it gets, and yeah, that is a problem. My final statement and my final analysis of where the losses come from and the gap in between cells and modules is delayed developments. So if we have, due to the reasons we just heard, different area devices, so with different PCEs at the moment, and then you come up, for example, with a development like exchanging a fullerene by an NFA, you get a rise in PCE on the square millimeter level. But this will be only delayed with devices on a square centimeter, and even further delayed with modules on bigger areas and then on square meters. So if, for example, we are now here at a point where, yeah, we have a rise and we see this steep rise in efficiency during the last 3 years. I think we had 5 absolute percentage points in record efficiency on a square millimeter level. This cannot be seen on the big module level yet, because those processes, they just need time. The materials are not available. They need to be synthesized on a larger scale, and so on and so on. So as long as there's a steep increase in the development on the square millimeter side, there will be a larger discrepancy in between the different device sizes. But no worries, in the end, it will get narrower again. And with this statement, I finish my talk. Thank you.